So here's the story. So what I'm going to talk about. Oh, sorry. Here it is. Okay, so I'm going to consider the Heisenberg-Weyl algebra from a purely combinatorial point of view. So first time what I'm going to do, I'm going to build a combinatorial structural graphs. I'm going to equip it with composition and decomposition rules. Then I will show you that this combinatorial structure has an internal bi-algebra structure, and even more. It can be given a half algebraic structure. And so this is here. And then I'm going to show you that if applied certain equivalence relations, I will show you that the Heisenberg-Weyl algebra, as well as the enveloping algebra of the Heisenberg-Weyl algebra, is a sort of a shadow of this more structural graphical algebra. So here is the story. And before I go forward, I wanted to sort of motivate you for this sort of pictorial reasoning, but I think that here in Computing Lab, most of the people are convinced that pictorial languages are much more easier to understand. I just wanted to give you just a very simple example. That suppose that you wanted to teach natural numbers to a child, how to calculate with natural numbers. Of course, you don't start with the axioms, with all these horrible things. You just say that instead of taking this, this horrible abstract concept, you can reason in terms of apples. You just have to explain that the color doesn't matter or the size doesn't matter, and that's enough. And that's what I'm going to do. So I'm going to take an abstract concept, which is a Heisenberg-Weyl algebra, or the enveloping algebra, and I'm going to provide you with an intuitive model, which in my understanding will be the combinatorial model of this algebraic structure. Okay, so first to gently start off, so maybe this I shouldn't show this. So where do you find the Heisenberg-Weyl algebra? So first of all, these are basic computational relations in physics. Then you find them in the second quantized quantum theory, and this of course all of you know, but maybe you might be a little bit less familiar that you find also this structure in combinatorics. That is, we have this structure which is satisfied by raising and insertion operator or certain combinatorial structures, and it translates into the world of generating functions later on. That maybe will show up in the end of the talk. So, what I'm going to talk about. So, what's the Heisenberg-Weyl algebra? To start off, to put some definitions. So, Heisenberg-Weyl algebra is generated by two letters, let's say A and A dagger, like the relation and equation operator, and with one relation. So, this is a free algebra with this relation factor out, right? So, this is the definition. So, all elements in the algebra have this form. These are strings in creation and annihilation operators with some finite sums with some factors here. And so this is the general element. Of course, this representation is ambiguous, so due to this commutation relation here. So what you do, you normally impose some ordering. And so for this talk, I will impose the normal ordering. That is, if you fix the preferred order with A dagger standing to the left and later standing to the right, you obtain this form. And now this form is unique. So these elements here form the basis in the Heisenberg-Weyl algebra. Some people may call it the Poincaré-Bukovic basis in the algebra. This is basically Poincaré-Bukovic algebra. This algebra is an associative algebra with unit, of course. And the structure, one can figure out what are the structure constants by multiplying two basis elements, which are here, and normal order this expression, and we can obtain this combinatorial coefficient, which I'm going to provide you with a graphical representation later on, a little bit. But before I will go to...
What's I?
Yeah?
What's I?
Where are here?
No, in the relation.
That's identity. That's identity.
That's just what.
That's identity, all right? Okay, so please ask me any questions during the talk. It will be much easier for me and perhaps more understandable. So, but before I go to combinatorics, I'm going to still provide with another more horrible structure, which is the enveloping algebra, which of the Heisenberg-Weyl algebra, Heisenberg-Weyl group. And what will that be for me? So the enveloping algebra will consist of, I'll have three generators now. I will additionally have this central element E, which of course commutes with other generators here. And then the enveloping algebra is again free algebra now with three generators, and with these three relations factor out. Again, we have a basis in this Heisenberg, in this enveloping algebra, and these are the nominal ordered forms in creation, annihilation, and this central element here. So what the advantage of this structure, with this additional central element is a Hopf algebra. Whilst the Heisenberg-Weyl algebra, as described before, is not a Hopf algebra, because co-unity doesn't go well with this relation here with identity. So that's the basic reason. I'm not going to talk much about this Hopf algebra. However, I'm going to just remind you what is the structure. Classically, we define the coproduct, which goes from the algebra to the tensor product, and it's classically defined on the generators, that is on these guys here in this form, in this way, and you can calculate what are the coefficients here on the basis elements. Then there is a co-unit, which is given in that form. It just extracts the coefficient at this for P, Q, and R equal to 0. And again, there is also an antipode, which is an antimorphism, which for some people is important. So this is an algebraic structure I'm going to talk about, and here is the picture. So I have the Heisenberg-Weyl algebra. I have a little bit more complicated enveloping algebra. So this is associative algebra with unit. This is a Hopf algebra. And you obtain the Heisenberg-Weyl algebra just by sending E to identity. All right. And so what I'm going to do? So I'm going to provide you with this combinatorial algebra here, which will be a Hopf algebra again, and show how this associative algebra with unit and this Hopf algebra can be obtained from here. So I'm going to provide you with two morphisms from here and here. And hopefully this will be much more intuitive than this abstract algebraic structure. So to start off, I'm going to give you a sort of vocabulary, combinatorial vocabulary. So directed graph is a collection of edges and vertices together with two mappings. So basically, this is a sort of a drawing. We have some vertices, we have some lines, and lines are directed. This is the directed graph. And for us, the pictures are enough. So we can forget about this formal definition. So directed graphs are just pictures with vertices and directed lines. So that's enough. These graphs will be embedded in the plane. So for this talk, whether this line comes from the left or the right matters, right? So they're embedded in the plane, right? So this is the first thing, and the second keyword here is a cycle. So the cycle is a path in the graph, which if you follow, you end up in between. So here are 1, 2, and 3 cycles, and this is not a cycle, right? So this is general vocabulary. I'm going to relax this definition a little bit. So I will call the Heisenberg-Weyl graph a directed graph in this sense I told you about previously. But I will exclude cycles. So I'm going to get rid of cycles. All right. So I forbid them. So this is the first restriction. And also I have to relax this condition of the directed graphs, and I will consider partially defined graphs. What do I mean by that? I mean that I'm going to allow that some of the lines may not have endings in the vertices. So some of the lines might have 3 endings. Though I don't allow to have a line without start and an end. Alright? So this is a generic graph, which I'm going to consider and call it a Heisenberg-Weyl graph. So if you look at it, it consists of 3 characteristic parts. First of all, there are inner lines here. This is here. I will call them gamma 0. And there are some lines which go out. I will note them by gamma plus. And there are some lines which go in here. And you can look at this picture as a sort of process, or a sort of a spider in Bob's language, or whatever. So there is something what comes in, and there's something what comes out, and there's something what happens in between. Alright? So this is a Heisenberg-Weyl graph. This is the definition. There is one very delicate concept, which is very crucial for this development. That is, we will need to define size of a graph. So, in general, size of a combinatorial object is some feature which, if you count, gives you a natural number. So, for graphs, that would be something like number of vertices, number of lines, which you count and obtain a number. So, for our purposes, counting vertices, counting lines is not enough. So, I will consider the size of the graph the number of its half edges. How can you see this? That is, I will count the number. I will count the inner lines twice. All right. So I count the lines, but the lines which are inside are counted twice. That means that I count endings of lines which are attached to vertices. In other words, or put it yet in another language, it is number of the half edges in a graph. All right. So this count as 1. This is the half edges, but these are, you can see there's one ending and the second one. Alright, so this is the size of the graph. Right, so I've defined the graphs. These graphs can be composed. How to compose these graphs? Suppose I'm given a graph, gamma 1 and gamma 2. There is something which is inside. And how to compose graph? So the simplest answer would be just to connect some of the outgoing lines from the gamma 1 with some of the lines which go into the second one, right? Of course, so this is a matching. So you just choose some of the lines here, some of the lines here, and just plug one into another. And here I introduce this sort of notation as a matching between some of the lines here and lines here, and a graph which is obtained by plugging these, plugging some of the lines here and here, like this. This means plugging, just plugging outgoing lines with the ingoing lines. Of course, there are many possibilities. If you are given a graph, you can compose them in many possible ways, depending on how many outgoing lines here you have, and ingoing lines you have here. So you can calculate them explicitly. That is the number of matchings of the number of matchings consisting of A pairs of lines coming out of here and I pairs coming from here is given by this combinatorial condition. So that's rather easy. So here's an example how that works. So suppose I'm given 2 graphs like x and y, and I want to compose them. So first I can make no connections. Just put one graph next to another. Then there's another possibility. I make one connection. So here it is. So there are 4 possibilities. Remember that the lines are distinguishable depending whether they come from the left or the right. Right? So there are four possibilities, and then there are two possibilities for making 2 connections. Right? So this gives me 7 graphs which can be composed according to these rules. That's composing x and y. So let's take another direction. Let's compose y with x. Right? So let's make this exercise. So there can be no connections, and there can be one connection. And one connection can be obtained in 2 ways. There can be 2 connections, of course, because y have only one incoming line. So here you see that there is this symmetry is broken. This will lead later on to non-commutativity. All right. So that's an example. All right. So this notion of composition have a few nice properties, general properties. So suppose that I give it two graphs, gamma 1 and gamma 2, and I will denote in this way a multi-set of all possible compositions. All right. So let this be a multi-set of all possible compositions of two graphs, gamma 1 and gamma 2. So first of all, this multi-set is of course finite. You can have a finite number of compositions. Then you can compose more graphs. Well, given three graphs, gamma 1, gamma 2, and gamma 3 somewhere here, you can first compose gamma 1 and gamma 2, and then with the results with gamma 3, or you can start with gamma 2, compose with gamma 3, and then from the bottom you can plug in gamma 1, and all of a sudden, what is the result? The result is that the sets which are obtained in the end are exactly the same. So this is this property. There's of course a neutral void graph, which is void graph, which if you connect the graph with void graph, you obtain the original one. Then there's no symmetry. We have already seen it. So composing gamma 1 with gamma 2 is not the same as gamma 2 with gamma 1. And this is an important property that this notion of composition is compatible with size. That
We could lower the screen of your laptop. It's easier for people
to
see the overview.
Yeah. Better?
Still.
Okay. Let me put it on the floor, right? Let me put it on the floor. Alright.
Shall we do? Take away the coffee.
Yeah, that's my coffee.
Thanks. Welcome. Alright, so what I was...
Can I ask something, Chris, interruption? You said the graphs are planar.
Yes.
So you've been drawing pictures where the edges cross each other.
Yes.
Isn't that related by polarity?
Yeah, well, okay, so I told that these are plane graphs, not planar, plane. So there can be crossing, okay? So in this terminology there can be crossing. So I know there are two schools and the terminology is not, established well. So there can be crossings, all right? But whether it comes from the left or the right, it matters, right? So that's important. That's why I want embedding in plane. Or you can view it also from another way, just that these are just graphs and all the lines are, let's say, numbered or something, all right? Okay, so this notion is compatible with the notion. So this composition is compatible with the notion of size. So what I mean by that the number of half edges, which is the size of the graph, is conserved when the graphs are composed, right? Here, and for this case, for example, counting the number of lines, just lines, wouldn't do. So you wouldn't have this relation. Of course, counting the number of vertices would do in this case. Okay, the number of vertices conserved, but then later on it will be eliminated by another property. But so the counting of the half edges is conserved when the graphs are composed. So this is composition of graphs. The graphs can be also decomposed. So suppose that I'm given a graph, and I want to decompose it somehow into, again, two Heisenberg-Weyl graphs. So let me take subsets of its edges, right here, these dashed ones here. So I choose this subset here, and when you look at it again, so this dashed, this graph with dashed lines here is again a Heisenberg-Weyl graph, and this remaining part is again a Heisenberg-Weyl graph. So the notion of composition would be just to choose a subset of graphs, choose a subset of lines, and take it as the left component, and the remaining part would be the right component. So the graphs can be decomposed in this way. Again, there can be many decompositions of a graph. that simple. And moreover, you can even calculate the number of possibilities. That is, so this is the number. If you want to number of possible decompositions such that you have I lines which go out, J lines which go in, and K lines which are inside, so this will be the coefficient, right? So you can calculate it rather simply. Here is an example, just to show you, to make this exercise. Suppose I'm given this sort of graph, just this beetle consisting of 1, 2, 3, 4 lines. So there should be in general 2 to the n possible decompositions. That is the number of subsets, and here are all of them. So so I can either choose to have no lines in the left component, then I can have 1 in 4 possible ways. Then I can have 2 on the left-hand side, and then I can have 3 on the left-hand side, and then I can have the whole graph on the left-hand side. So there is 2 to the n possibilities of decomposing a graph. Of course, some of these beasts here, like for example this one and this one, are exactly the same. So I will need to consider multisets, not sets, but multisets. So I will need to allow for copies of the graph in a set. And this is what I'm going to do. So let me denote it, so given a graph, let me denote it the multiset of all possible decompositions of a graph by this angled bracket. Okay, so this is the definition. And it has several nice properties again. I'm going to enumerate it one by one, because this is important for the proofs. You want to prove algebraic things rigorously. So first of all, it's a finite set, finite multiset, 2 to the n elements, where n is the number of edges. Again, we can decompose graphs. If given a graph, I can decompose it into triples, right? So I can first make a decomposition, then I can take the first component and decompose it, or I can take the second component and decompose it. And what I obtain so either way I go, I obtain the same multiset of decomposed graphs into triples. This will give me co-associative property later on. Then again, there is unique decomposition into the void graph. And there is this symmetry that is I can exchange the left component with the right component, and the multisets of possible decompositions are exactly the same. It means because it's just choosing complement of the original choice of lines in the first component. So so far I haven't mentioned about composition. So these two concepts of composition and decompositions are completely not connected so far. But here comes a very important and non-trivial property, which is rather rare when you think about composition and decomposition. That is, these two concepts are compatible. So what do I mean by that? From a combinatorial point of view, what does it mean? Compatibility and of composition and decomposition. So suppose I'm given two graphs, gamma 1 and gamma 2. And I want to split them into twos again, into pairs. So what I can do? So first, either first I can compose them, right? I compose them. I obtain some graphs, and then each graph can be decomposed into pairs, right? So this is the first choice. I can proceed in this way. But I can also do it another way around. That is, I can first, okay, so I'll have one graph and second graph. So the other choice would be, so let's split these graphs separately. So let's split this one and this one, and then compose them component-wise. So this means this way. And it appears that what I obtain in the end is exactly the same multiset. This is a very important property. This will prove that the algebra of graphs, which I will define later on, will be a bi-algebra. So this is the combinatorial counterpart of bi-algebra structure. Again, this notion is compatible with size. The size, I recall you, is the number of half edges. And I told you that composition was also compatible with the notion of with counting the vertices. So, but this decomposition wouldn't be compatible with this, with the number of vertices. As here I have 1, 2, 3, 4, 5 vertices, but here after decomposition I have 1, 2, 3, 4, 5, 6, 7 of them. So for our purposes, the right choice of the size of the graph is the number of its half edges, and it's compatible with it. Okay, so that's rather not important. Okay, so far I was concerned only with combinatorics, only with objects, composition and decomposition, but where's the algebra? So how to impose an algebraic structure on the graphs. So I define G because of the vector space G of graphs as a vector space which is spanned by the basis elements, which are all the Heisenberg-Weyl graphs, right? So here is the definition of the vector space. Of course, addition is defined as usual in this form. But what about composition? What about multiplication and co-multiplication? How can you define it, right? Here. So I had to provide you with some rule how to multiply graphs, and it's enough to give it on the basis elements which are on the graphs, right? So what is the definition? How to multiply two graphs. Since I know how to compose the graphs, so I will define the multiplication of graphs gamma 1 with gamma 2 in the following way. It means just sum over all possible compositions with coefficients equal to 1. So that's the definition of how to multiply two graphs. And here's the proposition, and so this multiplication provides me with the associative algebra with unit. So I have this structure on this vector space of graphs. Now I have also multiplication. It is non-commutative because there was no this symmetry when graphs are composed. What about coproducts? So I proceed in the same way. So I define coproducts just as the sum over all possible decompositions of a graph. And if I define it in this way, I obtain a co-algebra structure. And even more, I can define a co-unit, which just extracts coefficients standing at 1. That is, here is the definition. So co-unit of a graph is always 0 unless a graph is void. Right? So this is the definition of a co-unit. And this provides me with a bi-algebraic structure, and the main point in the proof of this fact is that this fact compatibility of composition and decomposition. This combinatorial property used here provides me with a bi-algebra structure on these graphs. So then I can recap a little bit. Here's the main theorem. So the Heisenberg-Weyl graphs, as I defined you, form a bi-algebra structure which is non-commutative and co-commutative, since decomposition is symmetric. But even more, I have a Hopf algebra structure that is with the antipode defined in this following way, which is just this alternating sum over all multiple decompositions of a graph, which is fairly standard in this Hopfology. And even more, I have a graded structure. I have a grading in the algebra, which is given by this notion of size. So what does it mean? So this is basically here. That is, multiplication of the graphs conserves the number of half edges, and co-multiplication in the algebra conserves the number of half edges again. So I have a graded structure here. So what I've defined for you, so far I've defined you a combinatorial algebra with intuitive notion of multiplication and co-multiplication, which is just composition and decomposition of graphs. Then I showed you that this algebra have a Hopf algebra structure as well as the associative AAU structure, of course, as well. So this is a Hopf algebra here. So what is missing? So this link is missing still. So now I'm going to show you that to come up with some morphism from this combinatorial algebra here to the enveloping algebra here and here, and possibly as simple as possible. So how to do this? Here is the definition. So I want to go from the graphs to the enveloping algebra. So I will show you this morphism, how to define this morphism. So the definition is very simple. So suppose you are given the graph, something like this. So the prescription is just forget about inner structure of the graph. So this means here. So I don't see what is inside. I just know how many legs are going out, how many legs are going in, and how many inner lines are inside. I don't know how they are connected. I know that there are some lines inside. So in this example, I have 3 lines which go out, 4 lines which go in, and 4 lines which are inside, though I don't know how they're connected. Right? And I send this graph into this element in the enveloping algebra here. So here's the definition in general. And here's the general theorem that this forgetful mapping, which forgets about inner structure of the graph, is a Hopf algebra morphism. So multiplication, co-multiplication, and antipode is preserved by this such defined morphism. So here's this theorem. And again, there is not a note if I further, so here I was just, I knew how there are lines which go out and go in, and I knew how many lines are inside. I forgot about the inner structure. If I further forget about the inner lines, the number of inner lines, I will end up in the Heisenberg-Weyl algebra here. So this is the definition here. So this is how to go from the graphs to the enveloping algebra, and this is how to go. Here. This is how to go from the graphs to the Heisenberg-Weyl algebra. So here is an illustration how it works. And suppose here is a picture. I've chosen 3 graphs for you. So how it works, and so this example I've already had on previous slide. So this is here again. So next let's suppose I take a void graph here. It doesn't have any lines, so it should go to identity, right? And let's take this graph here. So it should go to, it doesn't have lines which go out, go in, but it has 1, 2, 3, 4, 5 lines inside, so there should be e to the 5. And here again, I send e to identity here. So this is how these morphisms work. And how much time do I have?
Slightly over 15 minutes left.
15 minutes left. All right. So I'm going to skip this proof for the moment because I wanted to show you how to calculate with these things as well. So I'll skip it for a while. And so again, so here is the algebraic picture which I've shown you. So first of all, there is this combinatorial algebra, and there are these 2 morphisms. And here I have an intuitive notion of composition and decomposition. Here, all these guys here are rather horrible and algebraically developed. So what would be the partial conclusions? So that is more structural algebra of graphs can be seen as a combinatorial model of the Heisenberg-Weyl algebra. So this algebra here, with intuitive notion of composition and decomposition, can be seen as a concrete model of these 2 abstract structures here, which appear to be a shadow of this more structural algebra of graphs. Alright, so these are conclusions which can be drawn from this picture. But there's even more in this combinatorial development. I'm going to show you how to calculate with that. Alright? So let's take this morphism from the algebra of graphs here to the Heisenberg-Weyl algebra H here. So this is a morphism. So that means that we have this property which is guaranteed since it's a morphism. What does it mean? That multiplication on the level of graphs is mirrored by multiplication in this algebra H, in the Heisenberg-Weyl algebra. So if I compose two graphs, gamma 1 and gamma 2, multiply them together, that means that I just sum over all possible compositions. So on the lower level of the algebra H, what do I have? So I multiply these two these images of this graph here and here, which are like this. There are R2 lines which go out and S2 lines which go in. And there should be 1 and 1 here. So that's a mistake. But what does it mean on that level? That means that I have to calculate the number of possible compositions of graph gamma 1 with gamma 2. So, and this is the coefficient which stands which stands here in front of a dagger to the R, a to the s of this basic element. So instead of making these commutations, I can just enumerate graphs according to the number of outgoing and ingoing lines. This can be pushed further a little bit, and let's forget about such very complicated graphs, and let's take a graph which consists of one vertex only and suppose I take this base such an element of the algebra which is a sum over one vertex graphs with S and R outgoing lines with some coefficients which are inside. So on the level of graphs, if I take gamma to the n, that would mean that I would have to sum over all increasingly labeled graphs built of n vertices. See, so I need to have n compositions, built of n vertices of these types defined here. Increasingly labeled because I just build a graph one over another up to the nth step, of course. And increasingly labels means here that these labels here, that these labels follow the lines, of course. Right? So that's why I call it increasingly labeled graphs. So this is the nth power of a graph on the level of graphs. So again, on the level of algebra, so what do I get? So I'm just taking the nth power of this piece here, of this guy here, right? Of this element here. And on the right hand side, again, I have expansion in the basis with some coefficients which enumerate increasingly labeled graphs built of n vertices of these types defined by my initial choice, with k outgoing and l ingoing lines. So this is how to take power of take the power of this sort of extra element of the Heisenberg-Weyl algebra. And even further, if you take all these expressions all together, that is, suppose I want to consider exponents of this expression with some z which stands in front, you obtain a generating function of all increasingly labeled graphs built of n vertices, built of these building blocks. Here with z marking vertices, here, z is here, not the number of vertices, u marking outgoing lines, which later on will be replaced with a dagger, and v marking ingoing lines, which are annihilators, which come from the bottom. So exponentiation in Heisenberg-Weyl algebra comes down to enumeration of increasingly labeled graphs, which I described you, which are built of vertices of types given by this initial choice of an operator or an expression, which is given here. So why am I talking about this? At this stage it's very formal. So what's the advantage of this? So I'm talking about this because there have been there has been a lot of development in enumeration theory recently, in recent years, especially concerning generating functions and symbolic methods. I want to especially draw your attention to this book, this very recent book on analytic combinatorics and symbolic methods and generating functions, which was issued last year, and there's also a classical book by Pawel and Leroy.
Who's the first one by?
The first one is by Philippe Flageolet and Robert Sergelik. It was issued last year. So it gives a survey of these symbolic methods in generating function, and then you have a bonus in terms of enumeration, in terms of asymptotic behavior of the enumerated sequences, which is the second part. But I'm going to use only the first part concerning symbolic methods and generating functions applied to enumeration, because as I showed you, enumeration is important for this sort of calculus. And so I'm briefly going to give you a sort of vocabulary, combinatorial vocabulary. So suppose I consider a combinatorial class. That's a collection of combinatorial class of objects, which is a collection of objects. And I have some notion of size on that, and I want to enumerate objects which have size n. So let's Sn be the number of objects of size n, and then I need to, if I consider exponential generating function defined here, then it appears that all set theoretic constructions like the disjoint union, the Cartesian product, set construction, appending minimal, maximal element. These are just a few which I chose for the purpose of a few next slides. But there are many other, like the decomposition, sequence, derivation, etc. All of them consistently in a very simple way, translate into the world of generating functions. That is, if I'm giving two classes of objects, A and B, and I want to take a disjoint union, so what does it mean? This means just I add generating function. If I take Cartesian product, that means that I just multiply generating function. Then if I want to have a set construction on a combinatorial class, that's I want to consider sets of objects. That means just to exponentiate the generating function of this class. And again, adding the minimal element, which is not like this, means just to integrate the generating function. Yeah.
Well, what's the difference? I always wondered between generating functions and the undergraduate algebra thing of formal power series ring.
Yes, exactly. Well, because exponential generating functions from a combinatorial point of view are just formal series. So that's nothing more to that.
Yeah.
So
although in algebra it's a commutative ring, like many properties like polynomial rings, but this is different here.
This is different here. However, so the exponential generating series are formal power series, and you can define, addition, multiplication, derivatives, integrals, substitution, etc. on these things. So this is a huge, this is a vast knowledge of combinatorials which they have. So this is just to show you that such things exist if you're not familiar with. But I'm going to apply it to our example, to our stuff. I suppose I have 5 minutes. All right. Okay. So suppose let's take a very simple example: a dagger and a. Right. Let's take this expression here. So this corresponds to a vertex which has one line which goes up and one line which goes in. So what is the generic graph which is obtained according to the rules of composition, which can be obtained? So this is a generic graph. These are just lines which pile up, right? Lines with some vertices on the line, and of course all of them are increasingly labeled. So now, suppose I want to have an exponential of this a dagger a in the nominal ordered form. So what do I need to do? I need to find an exponential generating function. So how to do it in this modern combinatorial language? I observe first of all that this is a set of lines, right? Set of objects. And then what are these objects which are inside? These are again sets here, right here. So this is a set of some elements. And combinatorial specification of a generic graph would be as follows. This is a set of non-empty sets, which are here. And all of them, all these inner sets here, are additional labeled with U and V, as U is an incoming line. Here's a marker, and U is outgoing marker here, and V is an ingoing marker here. So this is no simpler than that. This is a combinatorial specification. You translate it into generating functions according to this vocabulary which I gave you. This provides me with the exponential generating function, and then finally I replace U and V with A dagger and A, and that is the normally ordered expression for the exponential of the A dagger and A. And it's no simpler than that. And then of course you recover from the generating function or this picture that this provides me this is a well-known structure of set partitions in combinatorials. Another example. Suppose I take now two building blocks, right? Here. So suppose I take A plus A dagger and I want to compute it. Okay, so A corresponds to incoming line to a vertex plus an outgoing line here, right? So that's A dagger. What's the generate graph? How does it look like? So first of all, I can make no connections, and I can have some outgoing lines from vertices. I can have some lines which go in, no connection. But when I make a connection, which is given here, I run out of outgoing and ingoing edges, and I cannot build up anymore. So this is third possibility. And again, this is a set of such objects. And how to compute that? How to make a compute with that in a combinatorial fashion? So what's the combinatorial specification of a generic of this combinatorial class? So this is a set of objects which are either lines which go out, right? Here's the label marker U as the outgoing lines are marked with U, or with I have ingoing lines or I have this sort of objects whose exponential generating function is here. This is just sets, this is specification. This is a set of two elements. Again, how this translates into the generating function. So here is the translation. So this exponential generating function of this piece here is just z squared over 2 because it's just one element of size 2. This is the exponential generating function. And then how it translates into the level of algebra. And here is the translation, and you can recognize well-known Baker-Carvajal formula on the right-hand side, left-hand side, and right-hand side. And again, what is the underlying combinatorial structure? These are B-colored involutions, because this is a picture of an involution, with single element, with singletons additionally possibly of two colors. That means B-colored involutions, that singletons are colored in two colors. So this is the underlying structure. And the last example, which I'm going to rush over, that is, let us take this sort of expression, A dagger squared A. So this is the building block here. What's the generic graph? This is just so this is a generic graph. They just go like this, like trees. And again, so what's the combinatorial specification? This is a set of trees which are forests in combinatorial language. These are forests of binary trees. This is combinatorial specification. And then how do you proceed? So either you know what's the exponential generating function of increasing the label binary trees, or again you use method of generating of symbolic combinatorics, and you write down the specification, etc., and then you come up with the exponential generating function of this, of forest of binary trees, increasing binary trees, and on the level of algebra you have this sort of expression, and well, these double dots are our usual normal ordered product, right? And there are many more examples. Many more examples which can be combinatorially handled. I just picked a few for you. this I'm going to finish. So we not only have a sort of an interpretation of the algebra, but we have a bonus, which is a combinatorial calculus on this level, which translates, of course, here down. Thank you.
So can one use the combinatorial calculus to address questions that people are directly motivated to ask down there studying?
Yes, precisely. That's what I'm saying. Yes.
So they would, I mean, such counting questions would come up naturally when people study, say, with a physical motivation?
Yes, precisely. Precisely. You can go, for example, so here, here I already, in the second example, where is this? Okay, no, here. Okay, it takes a while. Alright, stop. Ah, sorry. So, for example, here, well, this is a by example, of course. So, if you want to normally order this sort of expression, you normally do it with the algebraic stuff, like and this is a bi-algebra formula right here. But then, here you just obtain it in 2 lines when you know this symbolic combinatorics. Then you can treat some combinatorially. We can treat also much more involved cases like the quadratic expressions in the creators and annihilators, which algebraically is rather involved. But then, in this case, you would obtain, for example, just if you consider a dagger plus a dagger squared, right? So this corresponds to this sort of building blocks right here. And then, whenever you can recover a sort of pattern in a generic graph, like we did here, you can use this symbolic methods. So, for example, here, so the only possibilities are either I have zigzag like this, or with hands up, or like this with hands down, or I can have something like this, one hand down and one hand up. Or I can have a closed one. And then you can, if there is some pattern, you can always use these methods. So for example, for this case, it can be also easily done. The formula has certain applications, but in combinatorial way, it's really, really nicely obtained. And yeah, we can use it.
So you did the interpretation of the graph algebra to Heisenberg-Weyl algebra. You actually erased most of the structure. So I was wondering if you could give interpretations to other algebras.
Okay, well, it depends. For example, these graphs are also in position to where it is. So this is my last slide. So, for example, if you deform this Heisenberg-Weyl algebra, you take a Q commutator instead of ordinary commutator. So, exactly this very structure with some additional effort can be, so exactly this structure handles also the Q deformation of this algebra. We just have to provide a way how to obtain these, how to recover these Qs. But this can be very nicely done with this very structure. Concerning other algebras, I don't know. For SO3, I have no idea so far. But for example, for SU11, okay, whenever you have a representation of an algebra in terms of creation and annihilation operators, which in many cases is possible, you can use these graphs as well. However, I haven't looked at it, thoroughly. I haven't developed it to the end, but it should be possible.
So in restriction to algebras which you presented as creators and annihilators, is this algebra G then like the initial algebra in this category, or an initial object in that category?
But do you want to do this?
You're saying this combinatorial algebra G can represent any algebra which is presented by a creator and
Yes.
annihilator. So is it then the initial object in the category of such
Well, I don't know how to use this categorical language because I'm embarrassed to say that I don't know category theory, but perhaps yes. So that's
Hopefully,
my answer.
let's
Hopefully, yes. So my primary interest is combinatorics and this sort of algebraic combinatorics, but perhaps I hope that might give some insight into category theory as well.
The Hopf-algebra structure you have is very similar to, but also different from the primary normalization of algebra,
Yes.
right? So can you say something how they relate?
Yeah, okay, so there is relation. Okay, so first of all, I have to say that co-primacy is commutative and non-co-commutative, right? Whilst here I have, this algebra is non-commutative and co-commutative. But you can come up with a relation, how to relate the co-primacy algebras. So if you have we have this algebra G here. So if I consider a sub-algebra of commuting elements which are of this form, right? Which have some lines which go out and nothing which goes in. So this is a sub-algebra, and it's again commutative. And in this case, for this sub-algebra, you can come up with a very similar concept of decomposition, which wouldn't be co-commutative. Again, like the cuttings, etc., etc. And then if you reduce it, because again, con-primus algebra would be with this new co-product, newly defined co-product, would be a sub-algebra of this one, con-primus. Would be okay. I'll explain to you a little bit later. But, it's a little bit more involved. You have to change the co-product, and that's it. Which would be non-co-commutative, right? But still would be higher.
To lose the existence of normal forms, then it seems.
If
you have non-co-commutative.
Well, but the normal forms are actually it has to do with multiplication actually, and co-multiplication. So again, we have normal forms. Yeah, because it's multiplication is just this rewrite rule of the n-lates and creators.
Okay, one last question.
Have you looked into D-modules and cohomology of Heisenberg algebras?
Okay, so again, I'm embarrassed to say that I don't know much about this, but we could.
Because with your Hopf algebra structure, you almost have a cohomology theory on the algebra established, so it should be not too difficult.
Okay, it's nice to hear that.
Okay, so let's thank our speaker again.